So in the first part of this introduction, we looked at this differential equation, which governs the logistic growth, and we said that this is the solution to it. We're going to try and start with the differential equation and get the solution. So the first thing to note is that it is a separable equation. We've got 1 over p k minus p dp is equal to r dt, separate and integrate. Now what we have here are partial fractions with linear only in the bottom. So we've got 1 over p k minus p, and we can say, well, that's going to be the same as a over p plus b over k minus p. Going clear of fractions, 1 is going to be the same as a k minus p plus b p. So if we take p is equal to 0, we get 1 is equal to ka, and therefore a is equal to 1 over k. If I take p equal to k, I get 1 is equal to kb, which means that b is equal to 1 over k. And so over here, the left-hand side can become the integral. Let's put 1 over k outside here, of 1 over p plus 1 over k minus p dp, and that will be equal to RT plus a constant. We'll deal with that constant shortly. So we have 1 over k into ln p. I won't bother with the modulus because it's a population, it can't be negative. And then we would have, take away ln k minus p. And that's going to be equal to RT plus some constant. And so we'll have ln p over k minus p would be equal to kRt plus some constant. I'm just going to say that c is equal to ka there. Now I'll just pause there and I just remove the stuff on the right hand side of this because we've already used that. So we've got p over k minus p would be equal to e to the kRt plus a, which we can write as e to the a. Now when t is equal to 0, p is equal to p naught, and so we would have p naught over k minus p naught is equal to e to the a. So we've got p over k minus p is equal to p naught over k minus p naught e to the kRt. Now we want the solution to be p equals. So for ease of algebra, it might be best just to keep referring to this as e to the a for now. So we have p over k minus p is e to the a, e to the kRt. And so p is going to be e to the a, e to the kRt times k minus p, which gives us p is equal to k e to the a, e to the kRt, take away p e to the a, e to the kRt. And from there, we can say p plus p e to the a e to the kRt is equal to k e to the a e to the kRt. Now if we factor out the p, we've got p into 1 plus e to the a e to the kRt is equal to k e to the a e to the kRt. And therefore p is equal to k e to the a e to the kRt all over 1 plus e to the a e to the kRt. Now one of the things we do to simplify at this point is multiply top and bottom by e to the negative kRt. So on the top we just end up with k e to the a, and on the bottom we end up with e to the negative kRt plus e to the a, and that's it. Now let's take into account the e to the a now. We said was p naught over k minus p naught, and that's over e to the negative kRt plus p naught over k minus p naught. And at this stage, if we multiply the top and the bottom, so multiply by k minus p naught on the top and the bottom, then on the top it's just going to cancel out, and so we get p is equal to k p naught, and on the bottom we're going to get that cancels out, so we get a p naught, and then we're going to get k minus p naught e to the negative kRt, and there it is.